Awesome. Thank you, Rafna. Hi, everyone who's here. I hope everybody's enjoyed the conference so far. As Rafna said, I do enjoy cafe. So if anybody has any cafe suggestions, please leave that in the chat. Started. So before we actually start talking about differential privacy, I want to talk about why we need data, why differential privacy is actually important for us. So to be able to set the ground, let's talk a little bit about the real life applications of machine learning, right? So we see the applications of machine learning every single day in our lives. You see that in virtual personal assistants. So for example, Siri that you have on your phones, you have that on Alexa, any of your home devices, Google Home, and anything along those lines. You know that all these virtual assistants, it's backed up by machine learning algorithms and data. And you also see machine learning applications in recommendation systems, for example, in social media platforms. So for example, if you've ever been on Facebook or even on Twitter or even on Instagram, you get suggestions for people that you might know and posts that you might like. And it's usually based on the people that you've interacted with previously, things that you've liked, and the people that you are in contact with, what are they interacting with and whom are they interacting with. So based on that information, you get recommendations for that. And even on retail platforms. So for example, if you pick a particular book, you might get suggestions for, oh, other people also bought this book or bought these other books together. Maybe you want to try those out too. So these recommendation systems also come from machine learning, and also medical diagnosis. So for example, there's a problem based on the images that you see, what is the best diagnosis for that particular issue that you see. So the backbone of machine learning is data, is really good data. But getting access to data is not always easy because you have legal risks for institutions that will provide the data for you. And there are also risks about making sure that you want to protect the privacy of all of the individuals whose data is represented in the database. So let's look at examples for this. For legal risks, you can think about health institutions. If you want access to that data, they can't really do so because they are legally restricted from sending out that data to anybody else. And for example, you want to get data to all of the people in prison right now, you cannot do that either because they want to protect the individuals of the privacy of all of the individuals who are in the criminal database, for example. So getting access to data is not always easy and simple because there are a lot of guardrails to get to that data. But what is the problem that we run into when there's limited access to data? The problem that we run into is that people who want to solve complex problems, they don't get access to the data that they want. So for example, researchers and scientists who want to come up with better ways of diagnosing a particular issue in healthcare, for them, it's really hard to come up with a good algorithm that would actually help them solve without getting access to that data, right? So what's the obvious solution? The obvious solution to this problem is anonymizing data. So what is anonymizing data? Anonymizing data is being able to provide a database to people who are interested in the data, but removing all of the personally identifiable information, which is short for PII, which means that you are giving the data, but you're removing away anything that would link back to a particular individual. So for example, it could be your name, your address, date of birth, PIN codes, anything that could possibly link back to you, that will be removed and you'll be given access to the database. Turns out, anonymizing data is not strong enough. Let's look at examples for this. So in 2006, Netflix came out with a competition where they wanted the people who are competing to come up with an algorithm that would give us a better recommendation system based on what the users have rated the movies that they watched previously. So for this competition, Netflix released 100 million ratings of over 480,000 randomly chosen users from their database. And for people who don't really know, there's an independent database out there, which is called the IMDb, which is a website where you can go in and rate movies. Back in the day, you were able to look at the person's information and their ratings as well. So researchers and scientists, what they were able to do is that they were able to take the data that was provided by Netflix, and they were able to take the data from IMDb, the intersection of the users on both of these platforms, they were able to identify these individuals uniquely. Isn't that crazy? So even though one database did not have any personal information about any individual at all, just because of the other information that was available out there, you could tell who that person is, even though all their personal information was stripped out. So you might be thinking, oh, like it's not a big deal. What if you actually know a person's how much a person liked a particular movie or not? But turns out, based on the movies that you like or you don't like, and how much you like them, can tell what your political standings are. And this is something that not all of us want public. So this is obviously a privacy issue. This happened in another example as well, which was in Massachusetts, where the insurance was released, the insurance data was released for all the state employees, and this was cross-referenced by the voter data that was also available publicly, because of which the governor's data was medically recognized, and it was like uniquely identified. And now you see why anonymizing data is not strong enough. So what is the conclusion from all of this, right? The anonymizing data. We see that just because you're anonymizing a particular database, it doesn't mean that you're protected. It means that there's a possibility of other available data that's out there to be intersected with the anonymized data, where you can still be identified. And these are called linking attacks, by using two different databases and still linking them together to possibly learn more about an individual. So we need a stronger privacy protection policy, something that will protect the privacy of individuals regardless of what information is out there. So to tackle this problem, people started talking about privacy, right? So they wanted to define what privacy is, and this was the initial definition that was given. So what is privacy, right? So the initial definition that they came about with was, we could say that a person's privacy is preserved if the person analyzing the data does not know anything about the individuals in the data set. So for example, if I'm looking at a data set and all of you who are in the audience, your data is represented in the database, I will not be able to learn anything about you. But as you see that this definition wasn't strong enough and it was really vague. So they came up with a refined definition for privacy. And this went about saying that anything that can be learned about a participant from a statistical database can be learned without access to the database. What it means is that whatever I can learn from the database that I have access to, I could have learned that without access to the database. You see that this definition also has its own shortcomings. So for example, I cannot learn anything new from private data sets. So if you give me a data set that which just has like very personal information, I cannot have access to that data outside. So the previous definition of privacy that we see definitely fails that. And how do we know, because there's so much information available out there, how do we know if the data that I can access to the database is actually publicly available or not? That is also a loophole. And even if the information is available publicly already, who's to decide that information that is out there is good or is keeping people safe? So because of all of these definitions that they weren't strong enough, that's when differential privacy came into being. Differential privacy as a field was started by Cynthia Dwork, and she came up with the definition that you see. So differential privacy as a field, it makes a promise. It makes a promise that the data curator makes, that you, if I'm collecting all of your data, that you will not be affected adversely or otherwise by allowing your data to be used in any study, no matter what other studies, data sets, or information from other sources is available. So if I am in the field of differential privacy and I'm collecting all of your data, I'm making a promise to all of the subjects, the data subjects within my database. I'm making a promise to you that you will not be affected in any way at all, regardless of what information is out there. So there will not be any linking attacks that can link a particular data record back to you. So this is the promise and the definition of differential privacy. So how does this work? The entire backbone of differential privacy works on adding noise. And we can talk a little bit about this, but this is also, differential privacy is again split into two fields. Differential privacy, the first field is global differential privacy, where the output, where the noise is added to the last level at the global level, or the noise is added to the local level. So let's dig a little bit into this. So what is local differential privacy? So let's tackle that first. So local differential privacy, as I briefly mentioned, would be adding noise to the data entry level by the technique of randomizing responses or algorithmically introducing noise. So let's talk about the second part first. So algorithmically introducing noise, that means that if I am taking data from you and I'm putting it in the database, before I actually put your data into the database, I will randomly generate a number or any field that I can possibly add to each and every single value to the cells that I'm adding back to the database, and then I'm adding it back into the database. So algorithmically, I'm adding something in. So that is taken care of by the algorithm. But the second response, which is a really interesting way of doing it, is randomizing responses. So this method was actually borrowed from a field of social sciences to learn taboo behavior. So how does this work? This works. Let's actually walk through an example to understand how this works. So let's say I want to learn how many of you actually have shoplifted before. And this is like a taboo behavior, right? Like not everybody wants to like admit that they have shoplifted before. But what if I can give you some sort of plausible deniability? I'm going to tell you, okay, take these 2 coins, flip both of them, look at your first coin, and tell if it is heads, your first coin, give me the answer truthfully. Like whatever it is, if you've shoplifted, just tell me yes. If you haven't, just say no. However, if your first coin is actually tails, look at your second coin. If your second coin is heads, say yes, regardless to what the actual answer is. And if it is tails, you give me no. So what are you doing, right? By this process, I'm giving you some sort of plausible deniability. I'm giving you some kind of fence, which means that even if the data is leaked, you're still protected. So for example, if the data is leaked and somebody can in fact come back to you and tell you, hey, like, did you actually smoke? You can say, oh no, you know what? This was just because of the flip. This is the entire basis of how the data is actually being introduced into the database. This honestly is like a very interesting concept by itself. But you might be thinking, hey, so like all of the results that are going into the database, they're actually wrong, right? Like at least half of them are wrong. You're right, but you know how many answers are actually wrong. You know that because of the coin flip, you know that half of the answers are wrong, and you know the amount of bias that you're actually introducing. So because you're aware of the bias that you're introducing, you can reverse engineer the answer using the bias, and you can get a very close answer, which is awesome. So that's the basis of local differential privacy. Let's look at a little bit of code. Okay, cool, awesome. So let's look at this part, right? So what I'm doing here is I'm creating a database and the parallel of the database. I'm taking in the number of entries, which means what is the size of the database that I actually want to create. And the original, so it's passing in, it's returning 2 databases. The first database what it's doing is that it's trying to randomly generate numbers between 0 and 1. And if it is greater than 0.5, the cell value will be 1, otherwise it'll be 0. So in our case, the head is represented by 1 and the tails are represented by 0. So I'm just going to walk through the important parts of the code. So the important part here is like the original database that's being returned right here. Oh, hold on, sorry. Local differential privacy first. Yeah, so the same concept, we are returning the original database, which is the important part. So this is where the local differential privacy is. So let's walk through this code. So we're looking at a particular database, and we're saying, hey, you know what, just get the mean of the actual database. So the actual result of the database is being stored in the variable that you see. And then you're generating the coin flips. Coin flip 1, which means, hey, generate the same number of results as the database that was given to you in the query, and do the same thing. If it is greater than 0.1, it is actually 1 or 0. So it will, the values of all of the results in the first flip coin will be either 0 or 1. The same thing will go with second flip. So you have 3 databases at this point: the original database, the first flip coin database, and the second flip coin database. Everything of the same length, but the first one represents the actual data you're interested in. This first flip and the second flip databases are the coin flips. that will be used for the randomized responses. So this line right here, the one that I've highlighted right now, this is a noise-induced database. So you're taking the original database right here, and you're introducing the noise. You're saying, hey, you know what, multiply that by the first flip, which means that if it is actually 1, you will represent the data of the value as is. And this part will be negated because it'll be, since if the first flip is 1, this entry will actually go into the database, and this will be disregarded because 1 minus 1 will be 0, and this value that I've highlighted would be disregarded. That is only if the first flip is actually 1. If the first flip is not 1, and the second flip is 1, so this would be 0, and the second flip is actually represented in the database. So you see that the data that you're manipulating that and putting that into the noise-induced database. And then, you know, the bias that you're introducing. We told, as I mentioned before, the bias that you're introducing is actually half, right? So you're taking the result from the noise-induced database right here, and you are taking into account the bias that you're introducing, and the return result of the query is the one for the noise-introduced database, but with the bias introduced, with the bias accounted for, and then the actual result. So let's look at these, right? These results. So here we're generating a database of size 10, and then you're getting the result from the query, the data protected result, and the actual result is storing them, and I'm printing them out right here, the one with noise and the one without noise. So if I run this, you see that the results are pretty close. And then the results get closer as the size increases. So here you see that the size is 100, and if I run this again, they get closer, and the more experiments you run, the results get better. So the one with 1,000 results, they're even closer. So that's how local differential privacy works. And I hope the code helped you understand that better. So now that you've looked at it, let's look at the pros and cons. So with the biggest pro of using local differential privacy is that you can publish the data. As I said, because the noise is introduced at the local level, even if the data is leaked, the data subjects are still protected because of the possible deniability. The cons, however, is that it's a very data-hungry algorithm. As you saw, if the data set is small, you can still identify the individuals because the bias and the noise that you're introducing doesn't make up for it. So you need more data points to be able to come to a result that's actually close to the actual result and be able to protect the users, the data subjects in the database. So those are the pros and cons of local differential privacy. Now that you have gone over that, let's look at global differential privacy. So with global differential privacy, what you can do is that you cannot access the data directly. However, you can access the data through an interface. And the interface that you're accessing it through, that is what is adding the noise to the database. So actually, let's look at an example for this as well. Let's go back to the code. Yeah, so this is a part of the code that we're actually interested in. So this is the interface that you're interacting with. So this entire method, pretend that this is the interface that you're interacting with. So this has access to the database, the query in this case would be the sum of all of the numbers in the database, and the sensitivity. The sensitivity, you can think about it as the amount of noise that you want to have. You're taking that sensitivity and using that as a function to generate noise. And the result that you're actually returning is the actual query, the actual result plus the noise. So in this case, you see that the tensor is the, oh, hold on, let me actually run this from the beginning so that we actually see the results. DB, databases and parables is undefined. Hold on, let me just quickly fix this. Okay, cool, yeah. So the actual result is 518. And then when you run this, you're providing the database, the query, and the sensitivity that you're trying to run. When you try to run that, you see that with the noise being introduced, the results are actually pretty close. So the actual result is 518. and the result with the noise is 516. So if I run this again, the noise that's being added is random, because every single time you're actually asking the interface for results, because it's a random function that's generating the noise, every single time you get the answer that's random, but it's very close to the actual answer, which is 518. Global differential privacy works. So what are the pros and cons of global differential privacy, right? So the cons of global differential privacy is that you need to be able to trust the database administrator. So as you saw at the interface, the noise is being added at the interface level. So you need to trust the database administrator enough to make sure that they add enough noise to protect you perfectly. But the other con of global differential privacy is that you cannot publish the data. And the reason why you cannot publish the data is because your data is clean, and the data itself does not have any noise added to that. The interface adds the noise. But what are the pros? As you saw, compared to local differential privacy, global differential privacy actually gives you more accurate results. And you can, since you can tweak the amount of noise that you're adding at the last level, if you want to get really close to the actual result, you can think about the sensitivity that you're adding to be like really, really small, so that the noise that you're adding is also really small. So your results can be more accurate compared to local differential privacy. So awesome, like now you've learned what differential privacy is, what the two types are, how they work, but where is it being used? Is it just a concept? Turns out a lot of big company names are actually using that. So if you have an iPhone, you see anytime you type a text, you get suggestions for emojis that you might have used previously or for words that you've used previously. So obviously, recommendation system, as we spoke earlier, is based on machine learning and data as well. But the data that's being sent back to the servers at Apple, that happens only after adding noise at your device level. So they are actually using local differential privacy. So it means that anytime you type something, they want to be able to learn that about you, but they want to prevent your privacy. So they're adding local differential privacy and then sending back the data, so that your results, even though they can give you suggestions for what to type next, or what emojis that you want to use, or like what things that you want to look up based on your previous history, it's still protected. Your privacy is still protected. So it's also being used in the US Consensus Bureau to understand the commuting patterns of people. It's being used on LinkedIn for their advertising queries, and it's also being used by Google for understanding the traffic data. So as you see, people are using this in their real life. And now that you have learned how to do that, I hope you use it in your daily life too. So that's it from me. Thank you everyone for being here. Just a quick side note, I work at a company called Simple, and we are hiring. So if you're really interested in working with us, I highly recommend shooting me a message either on LinkedIn or sending me an email. I'll be more than happy to answer any of your questions. Thanks so much, everyone. If you have any questions, please feel free to leave them in the chat, or yeah.
We don't see any questions so far.
That's okay. If anybody has any questions, you can even message me later or email me, anything that works for you.
Yeah. Thank you everyone for joining the session. You can watch other sessions in the sessions, and thank you, friend. That was wonderful talk. I learned a lot. I need to look into it again to go through it and understand again what it's all talking about. But it was a wonderful one. So thank you. So everyone, you can check out Expo networking sessions, or you can watch other sessions. New sessions will be added by in 20 minutes. So I'll see you there. Enjoy the conference. Thank you.